All right. Here we go. We are on page 70, and we're ready for problem 7. So we have a distress flare shot straight up from the ship's bridge and all this stuff. Now, we need to kind of dig back in our memory bank because they don't give me an equation like they did in the problem above. Does anybody remember the projectile motion formula, the general formula for projectile motion? Alana?
Isn't it like 16t squared plus like velocity of t and then plus is it initial height?
Yep, that's exactly what it is. So instead of using y here, let me use function notation. And this is the projectile motion formula that gives us the height above ground at time t. Okay, we used this back in another chapter, right? Not like it looks familiar. Yeah. Okay. So they gave me all the numbers I need, so I just need to plug them in. So 75 feet above the water is the initial height. Initial velocity is 76 and negative 16t squared. Now, those of you that like, I don't know, study this kind of stuff, sometimes you'll see this exact formula, but this will be a negative 4.9, and that's the meters number. This is feet per second. If we're in meters, the gravity coefficient is a different number. But for us, we're in feet, so it's a negative 16. Okay. All right, so we're gonna graph this parametrically, I guess. So the key here is graph the flare's height against time. So in your parametric mode, let's go there. Make sure you're in parametric mode. And then y equals, I have to clear out the old ones. Where's your calculator? Okay, we get it out. Now, I want you to let x be time, so just t. So when we start, remember how last time we traced our points? Remember that? We hit the trace button and we watch the cursor move around? T, the t value is your time. That's going to be your time value, okay? All right, and then let's let y be this right here. So negative 16t squared plus 76t plus 75. Now, again, I kind of like to use just a regular window for x and y, but this problem is different, I can tell right off the bat. First of all, if x is going to be time, then x min isn't going to be my normal negative 10. What is x min going to be? 0, right? So x min is going to be 0. And then x max, now think of this, the flare is shot up into the air and comes back down. I'm going to go ahead and leave that at 10. I don't know how long it's going to take it. We'll find out when we hit graph. But I'm going to leave x max at 10. What's y min? What's the lowest that flare can go?
0.
0. And y max, now be careful here. Remember, it's already starting 75 feet off the ground. So it really doesn't make any sense to let that maximum be 10. So I'm going to pick a number like, I don't know, let's try 200. That's just a guess.
Ooh.
Now, I don't know, what did you put in for T min and max? I don't think we talked about that. Oh, let's try 0 to 10 and see what happens. Get graph and let's see. Oh yeah, did you get a nice little Parabola.
What were the equations of?
This is y, x is just t. Okay. Now, does the flare hit the ground? Where does the flare hit the ground? We can do this a couple of different ways. One way is to hit that trace button and to just move that cursor. And what would I be looking for if I want to know where it hits the ground? I'm watching those coordinates down there. I'm watching t and x and y. What am I looking for?
X is 0.
Not x to be 0, y to be 0. I want y to be 0. And it looks like it's 0 sometime between 5.5 and 5.6. Would you agree with that? Now, if I want to narrow that down more, remember how we can find zeros? We can hit second 0, second calc 0. What I don't know is, does that work when I'm in parametric mode? It doesn't work in parametric mode. So I guess I'd have to change it back to function mode, graph that equation to find the exact place where it hits the ground. You could also, by the way, use the quadratic formula and solve it to find out when it hits the ground. But right now I know it's between 5.5 and 5.6 seconds. Okay. Now, I want you to go back. Let's see, I'm supposed to do a couple of other things. I want you to go back to the problem. And let's graph it again and hit trace. Can you tell me when I hit trace, I went too far. I stopped my cursor randomly. I just stopped it. And I have t is 3.7, so is x, which makes sense because I set them equal to each other. And then y is 137.16. Can you interpret that for me? What does that point mean? Exactly. Isn't that what that means? Nothing fancy or weird or really that much different than when we're graphing in function mode. So, if I said to you, how high is it after 1 second? Could you tell me how high it is after 1 second? It is how high? 135. And then if I said to you, when else is it at 135? Could you tell me that? Maybe not super exactly, but where does it look like it's at 135 again? About 3.75 or so? Everybody see that? Move my cursor? Okay. All right, well, we got one more to do. One more, and it is number 8. Now, this one is different a little bit than the last 2 we've done. Remember when we had the guy walking on the horizontal line and we watched him go back and forth on the horizontal line? And then Larry or Gary or something like that. And then this one, we have a flare shot straight up into the air. And so this models its height above the ground. Well, read problem 8 and tell me what's different about it. What is different about the motion in problem 8? It's not what? Yeah, this motion is at an angle. This guy is hitting a baseball, and it's going like this. It isn't going straight up like the thing we just did, and it's not going straight this way like Gary or Larry did. This is going at an angle. So when that happens, you have a different parametric setup. The parametric setup looks like this. That's your x value. And then your y value is your projectile motion formula, but your coefficient on T, here in the middle, has changed. Okay? So this is the setup, this is the framework that you're going to use if your motion is anything other than horizontal or vertical. When our motion was horizontal, think back to Larry walking on that thing, we let X be whatever equation they provided us, but what did we let Y be? A constant. I can't remember what number I picked, but I just picked a random number and we watched them walk back and forth on that tightrope. When the motion was vertical, like the one we just did, what did we let X be? T. And then Y was our equation. When the motion is at a slant, X is the initial velocity times the cosine of the angle of the slant, and Y is the regular equation, except this, which before was the initial velocity, is now the initial velocity times the sine of the angle. Okay? So what will be our equations for this problem? He's 300 feet above the ground, so this is +3. That's your initial height. The initial velocity is 150, so, whoops, I need X. So X and Y. And X is going to be the initial velocity, which is 150. Cosine, do I know my angle? 18 degrees. T. So there's your X equation. Now your Y equation is -16t squared plus exactly the same thing with sine. We aren't going to be confused by that because throughout our study of trigonometry, X has been associated with cosine and Y is associated with sine. Now I do have a caution for you. When you put these in, first of all, you got to be in degree mode. That hasn't been a factor for us up till now because we haven't put it in Kansas. Got to be in degree mode because that's 18 degrees. Secondly, these parentheses that I have written here are necessary. Okay? So I know that when you hit this, you're going to get another set, and that's fine. You're going to have to double close. And the same thing here. All right, so get those equations typed in. Now let's talk about our window. If you struggle with this, it's probably because you're not typing it in right, so be very careful how you type it in. Try to type it exactly the way I wrote it. And make sure you're in degrees. Okay, anybody in here, who plays baseball in here? Okay, so when I hit the ball, how long does it take it to get over the fence? How long does a home run take? 4 seconds. All right, so for Team Men, let's put 0, and for Team X, let's put 5. I know it's power club, so it'll take me a little longer. Okay? We can change it, remember, if we need to. X-Men. Well, how far does this ball need to go? To a wall that's 400 feet away? So I guess I'm going to go from 0 to maybe 500, just to give myself a little bit of extra room. clear, or will the ball clear a 20-foot fence? So I'm gonna give myself a little extra room there. Let's take our Y maxes up to 50. I do not play baseball, so I don't know how high that goes. We'll try 50. All right, let's hit graph and see what happens. Oh, did you see the path of the ball? Oh, you should have. I got a nice little parabola. Well, you don't have your windows set right. I can tell from here, and I don't even have my glasses on. Okay, let's stop a minute, guys, let's stop a minute. We are all smart people. We need to be focused, and we need to be typing what Mrs. Ford says in the manner Mrs. Ford said. So, there's only one way you're not getting a picture, and that is you haven't done it right. It's operator error, the calculator is fine. Make sure you're in degrees. Make sure you have typed in an X equation and a Y equation look exactly like that. Make sure that your T's are 0 to 5, your X's are 0 to 500, and your Y's are 0 to 50. Now, those aren't set in stone, but they will work. They will give you a picture. If you do all those things and press graph, you will get a nice little parabola. Now, here's what I want you to do. Once you get your graph, I want you to hit that trace button, and I want you to follow the path of the ball. I want you to look particularly at the X's. Remember, the fence is 400 feet away, right? The fence is 400 feet away. So take your cursor till your X is about 400. Mine's not on exactly, mine's at 399. Get it to 400 as close as you can, okay? How high is the ball off the ground when X is approximately 400? 7.3 feet. Okay, now wait a minute. Did it clear the fence? No, because how high was the fence? 20 feet. 20 feet. So this ball did not clear the fence because after it traveled out 400, it was only 7 feet above the ground, and it needs to be 20 feet above the ground. Does everybody understand that? Alana, did you finally get a picture?
No, it's still not showing up.
Okay, it sounds like office hours tomorrow. Okay. All right, so that takes care of that. Good job. Now, I'm going to give everybody, I'm going to start passing this around. Everybody just take a couple sheets. And then if you, last person in the row, if you could bring up the extras, that would be great. Today, we are going to be graphing in polar coordinates. And you are
My phone's just slow.
okay. All right. So this is a big day. Take a couple pieces or one, I don't know how many. Come around. Okay. I feel like I haven't really taught you guys anything on here because everything we've done has kind of just been building on what you have known before. This is brand new. I finally get to teach you something brand new. Because up to this moment in your lives, everything you have graphed, including what we just did, has been in a what we call a rectangular or Cartesian system. In other words, your graph paper was a bunch of horizontals and verticals. And points were identified or plotted in terms of a horizontal and a vertical. So if I put a point right here, you would call that point 2, 1, because it's right 2 and up 1. That's a rectangular system. Right, up, right, down, left. That's a perpendicular rectangular system. Well, points can also be identified in a circular system. This is called a polar system. And if you've ever looked like at a globe from the top, you kind of see this sort of thing. This right here is the pole. So in a polar system, we call this the pole. In a rectangular system, we call it the origin, right? Now, points are identified in the polar coordinate system in terms of, just a minute, in terms of their distance from the pole and their angle in standard position. So this point right here in the polar system would be 2, because it's out 2 from the pole, comma, 30 degrees, or pi over 6 radians if we're measuring in radians. This paper I have set up in degrees, and these are 15-degree increments. So this one is 15, this is 30, 45. And that's just the way my paper is set up. Certainly it could be just like this can be set up with a smaller or a bigger grid. This can be adjusted too. And it goes all the way around. There's the point 2, 30. All right, let's look. Oh, plot 2, 30. Okay, did you do it? 2, 30. Plot 5, 5, negative 135. Well, remember, negative angles go this way. So this would be, if I'm going negative, this would be negative 90. And here's negative 120, negative 135 would be right here. So there's 5, negative 135. Now, a huge fundamental difference between rectangular coordinates and polar coordinates is, if I asked anybody in the world, who knows anything at all, to tell me the coordinates of that point in a rectangular system, everybody's going to say 2, 1. That's the only way to identify it. But in a polar system, if I said, give me the coordinates of that point, one option is 5, negative 135, right? That's one option. But isn't there, well, there are lots of other options, but isn't there one big option? How about 5, 225? Isn't that the same point? So in other words, there are infinitely many ways to name a point in the polar plane because of the idea of coterminal angles. Angles can be named in different ways, and so obviously polar coordinates can be named in different ways.
Could the x be negative 5?
Okay, first of all, it's not x, it's r. We haven't talked about that yet. But this is r, theta. R because that's a radius, right? A radius out. And theta because that's the angle. So his question is, can r be negative? And look at your point C. Oh, point C is negative 3, 60. Now, I know what you're thinking. You're thinking, wait, Mrs. Ford, if R stands for the distance from the pole or a radius, how in the heck can it be negative? Well, if the radius is negative, it simply means it's plotted 180 degrees different than the original angle. So in other words, a negative radius flips you to the opposite quadrant. So 60 degrees is right here. So 1, 2, there would be 3 comma 60. Flip it 180 degrees, and it's going to be at 1, 2, 3, comma 240. A negative radius simply means that you are plotted in the opposite location. So if the original angle is quadrant 1, you're actually going to plot it in 3. If it's quadrant 2, you're going to plot it in 4. It's 180 degrees difference. Okay, Jake? So that's how we handle it. Okay, so wait a minute. Let's come back. Remember we said there were 2 ways we could name this point? Now we see that we can also name it this way. Wouldn't that be the same point? Wouldn't that flip me 180 degrees to here? There are infinitely many ways to name any point in the polar plane. So that's what number 2 is asking you for. Number 2 says, okay, I have this point, 2 comma 100 degrees. Give me all of its names. So 2 comma 100, give me all of its names. Well, what else could that angle be besides 100? 460, how did you get that? At 360. In other words, you found the coterminal angles. So 100 plus or minus 360n. So were you listening to what Will said? He said that 100 can be named different ways by adding revolutions or subtracting revolutions. So this would be all of the points that had a positive 2. Well, wait a minute. What about the points that have a negative 2? Well, go back to the original. What would the angle be if we made the radius negative? Now remember, changing the sign on the radius moves you 180 degrees. So wouldn't one name for this be negative 2 comma 280? But of course it's not just 280, it's any coterminal angle for 280. To rename the angles, you add or subtract 360 in degrees, right? To rename the radius, to change the sign on the radius, you have to change your angle 180 degrees. Okay? So, I said there were infinitely many, there they are. There are infinitely many ways to name that particular point.
How come you only add to the 100 and don't like subtract? Like when you get to 100, can you just subtract 180?
Yes, that would make this angle negative, and we try to stay away from negative angles, but yes, you could. You could. Yeah. Alright, now, you knew this was coming. We got to change from one coordinate system to the other. Alright, so here we go. We have the polar coordinates 2 comma 120, and we need to change those into rectangular or Cartesian coordinates. Believe it or not, you've already done this. You've already done this. want you to look at what happens here. If I plotted that point, it would have a distance of 2 and an angle of 120. Would you agree with that? Would it look like this? So basically what I know is the magnitude of the number, which I've drawn as a vector, the magnitude of the vector, and its direction angle. And we talked about a couple days ago that x is always the magnitude times the cosine of the direction angle, and y is the magnitude times the sine of the direction angle. That showed up in that last parametric equation that we did, that idea. X equals r cosine theta, y equals r sine theta. If you don't already grasp that, please put a box around it, highlight it, that's important. X is always the magnitude times the cosine of the direction angle, and y is the magnitude times the sine of the direction angle. Now 120 happens to be an angle you can do without your calculator, right? So I know that the sine is √3/2, and the cosine is -1/2. So my point is -1, √3. Obviously, if you type that in on your calculator, you're going to get a decimal. That should be like 1.7 or something like that. This problem could be done without a calculator. If this angle had been 100 degrees, you would have to have a calculator, right? Or a table or something. Now that's easy. How about 3/117? Can you find the rectangular coordinates? That means the x and the y for 3,117. Sure. What's that? 3 cosine 117, and y is 3 sine 117. Gotta use the calculator. It's already set in degrees. That should be okay. You get -1.36, 2.67. It is that easy to change from rectangular, or excuse me, from polar to rectangular. Going the other direction isn't quite as easy, but it's still easy, and it's something you've already done. So I want you to think about this for a second. If I plotted the point 3, -4, it would look like this. If I made a vector out of that and built a little right triangle, your job is to find r and theta. You already know how to do that. Some of you didn't do it right in your homework when you were finding coordinates of your vectors, but I know you know how to do it when you think about it. This is 3, this is -4. This is r. This is r. Imagine a big circle here. This is r. Well, that's easy. Isn't that the Pythagorean theorem? So wouldn't r be 5? Now I need my direction angle. So what am I going to do? Second tangent 4 divided by 3. This angle is 53.13. I think that that may have actually been an actual problem in the homework. Because a bunch of you said negative 53.13, and that would be okay. Isn't that angle negative 53.13? Sometimes they do not. There are no directions here. But sometimes we stipulate that theta has to be positive. So if theta had to be positive, then we would take 360 minus that and get 306.87 degrees. But your negative 53 would also be fine. That's in standard position, the angle this thing makes with the x-axis. So here are one example, one form of the polar coordinates. And let's try negative 5, 1.
We just have to find one of them.
Yeah. Or unless it says one more. Negative 5, 1. Remember, you're changing to polar, so you need an R and a theta. All right, that's easy. What's R?
324. 26.
There we go. Root 26. And this is theta, kids. This is theta. So when you do second tangent 1/5, this time you'll have to subtract that from 180. And I got 168.69. Have you? Everybody okay with that? Okay, gang. In number 5, we have polar equations. And we are going to be graphing these, spending some time with these tomorrow or next time. Maybe even today. We're doing quite well. We might get to it today, but probably not. Right now, though, you're going to take this polar equation and you're going to write it as a rectangular equation. Now, make sure we're clear on that vocabulary. This is a polar equation because what are its variables? R and theta. That makes it polar. If you want it to be a rectangular equation, then you've got to get, somehow you've got to change all that R and theta to X and Y. Right? So I want you right now to think back in your deepest memory, back when we first learned that cosine was adjacent over hypotenuse, and then I threw at you an alternate definition. What was the alternate definition for cosine? Not adjacent over hypotenuse, but what? X over R. So I'm going to change this cosine theta into X over R, because that's what cosine theta is. Sine is Y over R. If I clear the fraction by multiplying by R, like I always do, get rid of fraction, now I have this. Now I am not done, because what am I trying to do? I'm trying to write an equation that has just X and Y. If I plot a rectangular thing, isn't this X and this Y? And I would call in my hypotenuse R, about x squared plus y squared? What does x squared plus y squared equal? R squared? X squared plus y squared equals r squared? So I'm going to change that r squared into x squared plus y squared. Is that a rectangular equation? Yeah. What are its variables? X and y. Anybody know what shape that is? It's a circle. It's a circle. It is not centered at the origin because of this guy. This guy has shifted it, but it definitely is a circle. Absolutely. I just can't wait. Let's just give it a shot. Go to your calculator. Go to mode and change it into polar. Okay, you got it in polar. Okay, so now go to y equals, and now it doesn't say anything that it's ever said. Now it says r equals what? So type 4 cosine theta. This is 4. Where's the theta button? Press your variable button, and theta's there. Now before you hit graph, I am still in degree mode from the last problem, and that's fine. But when I go to my window then, theta min will be 0, and theta max will be 360. Does that make sense to you? If I'm in degrees, I'm going to go all the way around. If I were in radians, it would be 0 to 2 pi. Now, please listen to me. This is going to save you some headaches. Theta step. We haven't spent a lot of time talking about that step thing, but I need you to change that to 5. Oop. Try that again. Take a step. Change that to 5. Okay? Now, for x, min, and max, let's just go with negative 10 to 10. Those are kind of big numbers for this problem, but that's what you would normally just choose your standard negative 10 to 10 and hit graph. Did you get a, well, it's supposed to be a circle. Does it look a little ovalish to you? I use negative 10 to 10. All right, so let me show you another little trick real quick. If you want to know, I think we may have talked about this before, but I'm going to say it again. If you want to know exactly what this is, you have to hit zoom 6. No, 5. Zoom 5. That's zoom square. What zoom square does is creates a setup that squares the rectangular screen. When they made your calculator, and I don't understand this, they made it a rectangle. So everything is automatically stretched horizontally. If you want to undo that, you hit zoom square, and that will give you a square picture. This is what it actually looks like. Okay? Now, I want you to go back to window, and I want you to understand what that step does. Have we talked about this before, what that step does? Because mine was originally set at point 1. Go ahead and make your step point 1 and hit graph. It's going, but it's going really slow, right? So again, I need you to understand that your calculator is plotting points. Actually, your calculator is plotting points. And you have asked the calculator to go from 0 to 360 in increments of 0.1. So in other words, it started at 0, and then it did 0.1, 0.2, 0.3, 0.4, all the way to 360. Do you understand why it's taking so long? That's a lot of points. And it's plotting them one by one. So when I had you set your step at 5, then it's plotting like this, which is a lot faster, but it's also a lot fewer points. What is the advantage to leaving the step at 0.1?
It's more accurate.
More accurate. You get a great picture because you can plot it as so many points. But what's the disadvantage? It takes forever. Okay? So, mine finally got done. Oh, actually, it's not quite done yet.
It's gotta be less than 30.
Oh, mine isn't working. It's not.
All right? One more thing. Set your step at 30 and hit graph. Now, did it go fast? What's the downside? It's got some straight edges, right? You didn't plot enough points. So one of your jobs as you graph these things is to figure out what your steps should be to get a decent picture without taking forever. My advice, at least as a starting point, is if you're in degrees, use a step of 5. If you're in radians, use a step of 0.1. That's a good starting point. There will be a few graphs that won't work on, but for most of them, that'll be fine. Are you guys even listening to me?
I'm trying to figure out how to stop the calculator. Once it starts yelling, it won't stop.
Okay. Can you second quit or second turn it on? All right, let's do the same thing. So, by the way, this was our equation right here. That was a circle, we figured that out, we graphed it, it was great. Next one. R equals 3 cosecant theta. Start the same way. What did I do first over here? Change my cosine into x over r. So what do you think I'm going to do here? Change this not into r over x, but r over y. So r equals 3 r over y. Then I'll clear a fraction just like I did before. So ry equals 3r. I'm going to break one of my own commandments. I'm going to divide by r. And I'm going to do y equals 3. Now, normally I would be having an absolute hit if you divided by a variable. R is a variable. Why is it okay? Okay?
R can't really be 0.
It can't be 0. If r is 0, where am I? If the radius is 0, aren't I at the pole? So I'm not going to have a graph anyway. So r can't be 0. Is that okay with everybody? So I'm going to divide it at y equals 3. What's the shape of this equation? Not just a line, but it is a horizontal line. It's a horizontal line. I see some of you are checking that right now. God bless you. Fisher, wake up, sunshine. This stuff is fun.
Too late now.
All right. One more. R equals 2 sine minus 4 cosine. My job is to change this into a rectangular equation. What do I do first? Guys.
M all to y over r, r
So
over y.
sine is y over r, and cosine is x over r. What if my problem had a tangent in it? Y over x. Can't all of the functions be rewritten? Yes. All right, what do you think next? Multiply by r, so r squared equals 2y minus 4x. Then what? R squared, remember, is x squared plus y squared. Guess what? You have another circle. But this one has not just been moved sideways, this one has been moved sideways and up. Right? So let's graph it, make sure that happens. We did a lot of messing around, or I did anyway. 0 to 360, my window, or my set is 5. I'm just going to go with negative 10 to 10.
Is it still in polar?
Huh?
Is it still in polar?
Yeah. We're graphing our polar equation, so we're graphing this right here. You can't graph this without doing a lot of work, because you got to have y by itself if you're going to do it rectangularly. So I'm going to graph it in polar. So I changed everything back. Don't forget to close the parentheses after the thetas. Remember, if you're not happy with the shape, you can square your screen, zoom square, and you can also change your steps. If you think that, mine actually has a little jaggedy look to it, so I might change my step and see if that helps it. Takes it longer, obviously, but yes. And can you see a circle that is not centered around, or not symmetric about either axis? It's moved to the left and slightly up. That's what's going on here with the y's and the x's. Perfect. Now we're going to go the other direction. We're going to write this as a polar equation. All right, I erased it. What did I have right here? You can still kind of see it. X equals r cosine theta. So I'm going to change that to r cosine theta. And that's my polar equation. If I wanted to graph it, I would write it as 3 over cosine theta. Because when I graph it, it has to be r equals. And would you stop and think about this for a second? You're all just tired, you're all watching the clock. Think about this for a second. Can you graph that on your calculator? In rectangular mode, I mean? In rectangular? How do you put that in? It's got to be y equals. This is not a function. So it's not graphable in rectangular mode. Is it graphable in polar mode? Absolutely. Absolutely. So the benefit of these different modes is you can graph things that you couldn't graph otherwise. All right, r equals 3 cosecant theta. Oh wait, I already did that. 2x minus 3y equals 5. I'm rewriting it as a polar equation. Any ideas? What do you think?
Switching to R cosine.
Exactly. Guys, this is the easiest problem you're ever going to see in your whole life. Ever. Because what is X? R cosine theta. What is Y? R sine theta. Kids, it's a direct substitution. Is that a polar equation? Yes. Now, if you had to graph that polar equation, you would need to get R by itself because that's how you put it in. So let me say, this is a polar equation. If the directions are right as a polar equation, you have done it. But if you have to make that equation graphable, you're going to factor out the R and divide. So in other words, if you want to graph your equation, once you have changed it to polar, if you want to graph it, you got to get R by itself. So you would pull out the R and then divide by that parentheses. Does that make sense to everybody? It's pretty easy arithmetic. What shape, if I actually type this into my calculator, and by the way, just like always, leave parentheses down there. If you type that in, what shape would you get? A line. That's just going to be a line. It better be a line. Right? Changing from rectangular to polar does not change the shape of the picture. All you're doing is changing your coordinate system. You're not altering. All right, one more. Now we need to simplify our work a little bit too. So I think, let's FOIL and see what happens. So we have x squared plus 6x plus 9. I'm foiling. And y squared plus 6y plus 9. Okay. What happens to the 9 and the 9 and the 18? So we have x squared plus 6x plus y squared plus 6y equals 0.
Switch it to R squared.
These two make r squared. Is that a polar equation? No, because it's still got x's and y's. How am I going to get rid of those? Direct substitution. So r squared plus 6r cosine plus 6r sine equals 0. Are you with me? Is that now, this right here, a polar equation? Okay, suppose I had to graph it. Is it graphable? If you're going to graph it on your calculator, you have to have R equals, don't you? Any thoughts on that? What? Mallory, what'd you say? One of you? Can I divide by R? Well, I'm the teacher, I really don't want to write. No, I can divide by R because it's not 0. So now look at it. R plus 6 cosine. That should be a theta. Plus 6 sine is still equals 0. Can I get R by itself? So R equals -6 cosine minus 6 sine. Will that go in my calculator okay? And it will be a circle. Tonight, when you sit down at the dinner table with your loving family, and mom says, as mothers always do, "What did you learn in school today?" You can say, "Oh, Mom,